Okay, now we're going to talk about Chapter 4, probability. And to start, we'll start with an easy concept of flipping a coin, right? So if we flip a coin, you have two options. You can get either heads or tails. Well, what if we flip three coins, right? So one option is heads, heads, heads. Right? We flipped it once, got a heads, flipped it twice, got a heads, flipped it a third time, and got heads. Another option would be heads, heads, tails. Or heads, tails, heads. Or tails, heads, heads. Or tails, tails, head, tails, 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 heads, tails. Or, when are we missing here? Heads, tails, tails. So 8 possible outcomes, right? So let's get us into our first definition, right? Each one of these things in the curly brackets is called an outcome. And when we flip a coin 3 times, we have 3 separate outcomes. And because this is the total of all outcomes, this is called our sample space. Right? So, the big thing with probability is making sure you define an event. Right? So if we go to the next page, and we'll say, let event A be I flipped exactly 2 heads. Right? So if we go back to the previous page, we can see our sample space. We want to count how many times we got exactly 2 heads. So this one has 2 heads. This one has, come on. Oh, my stylus is being finicky. 2 heads. This one has 2 heads. And that is it. So we want exactly 2 heads. So there's 3. So we have 3 outcomes with 2 heads. So if we want to do probability, well, probability of some event equals success over total. So total, just like it was back in chapter 3, is our little n, our sample size. And success is that our event happened. Success doesn't always have to be good. For example, if you are chasing tornadoes for research, every time a tornado touches the ground is a success for your event. And typically, when a tornado touches the ground, is not a good thing. So we got to not think of the success as a good thing, more as success is whatever you were looking for has happened. So, let me erase our little n here. In our example, we had 3 outcomes where we had exactly 2 heads, and we had a total of 8 outcomes. 1, 2, 3, 4, 5, 6, 7, 8. So the probability of getting exactly 2 heads is 3 out of 8. Alright, so let's do another one. What is the let event be that I have no heads? Alright, So the probability of B, again, is success over total. So we come back here. This is the only one that has no heads. So it is 1 out of 8. 1 out of 8. Another way to do it is using the complement rule. The complement rule says the probability of event A plus the probability of its complement, with the line above it, will always equal 1. And all complement means is the opposite, right? So, if the probability of event B is 1/8 of getting no heads, well, the complement will be I get at least one head. So if we go back here, how many have at least one head? 1, 2, 3, 4, 5, 6, 7. So 7 over 8. 1 over 8 plus 7 over 8 equals 1. So the complement is a rule that we'll use quite often, where sometimes when you're looking for something, it's easy to actually find its complement. Alright. Let's do... let's find an easy one here for... Alright, let's just talk some of the rules. So, the probability of any event has to be greater than equal to 0. Right? So we cannot have negative probabilities. All probabilities are positive. The probability of the sample space, which is the probability of all your outcomes, will equal 1. Which goes back to why we have the complement rule of the probability of an event plus the probability of its complement must also equal 1, because the probability of its sample space is 1, and the probability of an event has to be between 0 and 1. Alright. As long as your events are equally likely, the probability of an event is success over total. Another good formula to know is when you have the probability of A plus the probability of B minus the probability of A and B. This equals the probability of A or B. What does that mean? Well, say if we have, let me find a nice example here to do. So I'll do one in the book. That way, if you want to look in the book, you can kind of follow along with what we're doing. Okay, this is a table out of the book, table 4-1 on page 132. We're going to use this to kind of do some things. So, you have subject uses drugs, subject no drugs. Then you have positive test results, and then 45 of the people that use drugs get a positive test. 25 who do not use drugs also get a positive test, right? This is called a false positive. So, the top row, positive test and negative test, says the test says they do drugs. The column on the left, the subject uses drugs or does not use drugs, that means you know if you use drugs or not, right? So, if we first want to find the probability that someone uses drugs, remember that success over total, if you add up all these numbers, there's 555. And so if someone who uses drugs is the 45 plus 5, which would equal 50 over 555. And you can simplify that down to a better fraction, or you can put it in percent form, which would be 9%. You could also find the probability of a negative test. And that would be 480 plus the 5, so these two numbers, over 555. Simplify the fraction down, or put into a percentage, 87.4%. All right. So, what if we, let's see how do I do this without losing on my whiteboard here. Much easier in the classroom when I have much bigger space to write. All right, so if I take this to the next slide, and all right, I'm gonna have to erase this because I don't want to lose my photo. So, clear drawings only. Perfect. Now, what do we want to find the probability that someone uses and test positive? Well, that would be this number right here, right? This is why tables are so good, because this is someone who uses and tests positive, so it is just 45 over 555, which equals 8.1%. So using this example, we can finally practice using the addition rule. So what if we had probability someone uses or tests positive? Well, we already did uses before. We said that was 55, I'm sorry, not 55, 50 all over 555. The probability that someone tests positive is 45 plus 25 all over 555, right? This column here. That's people test positive. So this is the probability of event A. This is the probability of event B. And then remember the formula says we have to subtract out their and. And A and. This is A and B. Right? So where are the person that uses drugs and tests positive? That is this number right there. So I have to minus out the 45 over 555. And the reason for that is it's been double counted. We counted it going this way, and we also counted it going this way for the 50, so we double counted it, so we must take it out. And if you do all the math out, you get 75 over 555, or 13.5%. Alright, so clear all that. No, clear drawing only. So another formula to add, and these are on the little pullout if you actually got the tech ebook. If not, you definitely want to go through and make notes. If you're using ebooks, you didn't get the little pullout that comes in the actual textbook. The probability of A with this line, which means given, B, equals the probability of A and B all over the probability of B. Notice, whatever is in this spot here, it is what's in the denominator, and this whole thing just becomes an and. So if we go back to our problem, and we do the probability someone uses given they test positive, right? We already did uses and test positive before. That was 45 over 555. And then the probability that someone tests positive is do we do that one? So those he just uses and the test positive. Oh, here we go. Test positive with all these guys again. Remember that it was the 70 over 555. And when you simplify this down, you get 45 over 70. Another way to think of this, though, is when you have a given, right, when you have this symbol, given, that means you are updating your probabilities based off something you know. So therefore, instead of using the whole sample space now, all we care is about is this column, because we said given they test positive. We don't even care about the people that tested negative. We only care about the people that tested positive in the red box. So now our new total is 70, and the probability it uses is 45. So probability frustrates some people because you can easily get the answer sometimes by thinking through it logically, and then other times it takes, or you could use the formulas. There's lots of ways to do probability. There's lots of wrong ways to do probability. But these are kind of the keys to doing probability. Alright, so one of the last things I want to put into this video is the rule of independence. So, a couple ways to show this is with what we call a Venn diagram. So I'm going to draw a couple Venn diagrams and put up the formulas, and then I'll probably save this video. So you got event A and event B. Alright, so a Venn diagram is just a box of the sample space with your events inside. So if your two events do not touch, they're called disjoint or mutually exclusive. I think I have an extra Y in there. What does that mean? That means the probability of A and B equals an empty set. Doesn't exist. However, we could have another sample space. Oops, not money symbol. Where A and B do touch, and the part where they touch, that is A and B. If you can draw a Venn diagram for any one of your problems, the neat thing is the probability of A or B is everything inside the two circles. And then the part that's mutually exclusive is the stuff that's outside. Right, so the Venn diagram is a good picture way to show these things. However, another thing I wanted to talk about is if two things are independent. Things are independent if the probability of A times the probability of B equals the probability of A and B. All right, so an example of this is flipping a coin. So I can get, if I flip a coin, the probability I get heads on the first try is 1/2. I can get a heads or a tail, so 1 success, 2 tries. Well, the probability I get heads on so put a little 1 there, a heads on a second flip, right? It's the same coin, it's still 1/2. Well, the probability that I get 2 heads, so H1 and H2, that's right, I went to write B instead of H2, right? Well, that is 1/2 times 1/2, which equals 1/4, right? So that says the two events are independent. Well, let's just prove that real quick. How many different ways can you flip 2 coins? You can have a heads heads, heads tails, tails heads, tails tails. Well, how many of them have 2 heads? 1. How many outcomes are there? 1, 2, 3, 4. So 1/4. These two things are equal. Therefore, flipping a coin is independent. There's a lot more to 4, so please read over it. I will post another one of me kind of solving some problems for the homework using probably Excel. StatCrunch really doesn't help you here. And I'll cover a couple more of the concepts in that video as well. Definitely want to read over the chapter. A lot of the examples in this section use this table, so that's why I wanted to include it in the video. Please email me if you have any questions.